Hello everyone, I am Prajit Krishna Kumar. In this video, I am presenting our paper titled Fast Decision Support for Air Traffic Management at Urban Air Mobility Vertiports using Graph Learning. Urban air mobility represents a revolutionary approach to moving people and goods within cities using aerial systems. At the forefront of this movement are electric vertical takeoff and landing aircraft, which can ascend and descend vertically like helicopters, but are quieter, more sustainable, and potentially more scalable. These innovations have the potential to reduce urban congestion, transform city logistics, and offer a new mode of rapid transportation. Skies might be soon filled with eVTOLs, but they need a place to take off, land, and recharge. We call that place a vertiport. Vertiports can be rooftops of any building or can be in individual stations. Consider an individual vertiport station. We will have hundreds of vehicles entering and leaving the port in span of an hour. Similar to an airport, we need an air traffic controller to give them instructions. In an vertiport, it is difficult for a human to control them, and this becomes more difficult under the presence of uncertainties such as weather leading to safety concerns. The primary contributions of this work lies in formulating the urban air mobility vertiport management problem as small code decision process and development of relatively realistic virtual environment to simulate this MDB for scaled-down multi-rotor vehicles. Testing the hypothesis that a graph abstraction of the state space along with graph learning can yield effective policies for this problem. Analyzing the trade-offs between objectives such as takeoff delay, landing delay, collision avoidance, and battery conservation achieved with such graph learning-based policies. In our problem, we consider two normal ports and one battery port. We simulate four eVTOLs. Once the eVTOL takes off and leaves the port, the morphology is taken by other vehicles. This keeps the vehicle count to 4 at all times. The objective is to maximize the safety, minimize delay, and manage battery level. We formed two graphs, one for vertiport states and one for eVTOL states. The vertiport states consist of availability, type of port, and its location. Similarly, the eVTOL states consist of its location and other properties. At any instant, the policy can provide actions to take off, land, move, or avoid collisions. The reward function consists of 5 terms: takeoff, landing, delay, battery, and safety. Each term has weights which indicates the importance. We consider safety to be the most important, and the weights are set to maximum for safety, followed by other terms. Two frameworks are used for learning the policy model, namely the multi-layer perceptron-based oral network and graph learning-based oral network. Both frameworks have feature abstraction policy and value networks. The main difference lies in the feature abstraction network, where the oral agent uses a condensed feature vector with both the vehicle and vertiport state space. The GRL agent uses two graph convolution networks or GCNs, which takes the vehicle and vertiport feature matrix along with the respective edge connectivity matrix. Both the policy networks will use 4-layer MLP with log softmax. To create a simulation environment, we use Unreal Engine along with AirSim for flight dynamics. On the top right is the working of simulation, and at the bottom right, we have the simulation framework. OpenAI Gym environment is created to facilitate the communication between AirSim and oral algorithm. While the AirSim takes care of movement of vehicles, the parameters such as battery and schedules are coded externally. Here is the hardware deployment of the trained GCN model. We used crazy flies to simulate the vehicles in motion capture environment. At the time of initialization, all the vehicles get a random schedule and move to the respective positions. The policy then divides the actions for each vehicle sequentially. In the simulation environment, the actions execute in parallel, while in hardware demonstration to avoid any crashes, new action is taken after the previous action is complete. For comparing our policy, we use two baseline methods: feasibility preserving random walk and first come first serve methods. In the feasibility preserving random walk method, at each time step a feasible action is taken, we don't consider delay, battery, or safety. In the first come first serve method, whichever eVTOL comes first gets its preferred space. We trained our oral model for 1 million time steps with PPU algorithm. In order to evaluate the performance, we performed two case studies. The left plot shows the testing results of the trained model for 50 episodes, that is 72,000 steps. Here we consider takeoff landing to be good when it takes off or lands within 2 minutes of the schedule. GRL agent has zero collision and but has battery. This two has the highest weights in the reward functions. The first come first serve agent has good takeoff, landing, and less delay, while it has few collisions. The oral agent, while can avoid collision, it didn't perform well in other cases. Due to GRL's better feature extraction, it outperformed MLP-based policy. In the second case study, we analyzed how the weights of safety coefficient affects the learning outcome. We trained another GRL model with the weights of safety coefficient as 0. The plot on the right side shows the results from 50 test scenarios. The model that is trained without safety coefficient has more collisions. Overall, to conclude, we propose a graph learning method to generate a policy that serves as a real-time air traffic controller system at a vertiport. We formulated the UAM-Vertiport management problem as an MDP. We use two GCNs to extract the vertiports and aircraft state information as learnable feature vectors. GRL policy performance is compared with three baselines. Due to GCN's better feature extraction, GRL outperformed MLP oral and other baselines. In the future, simulation based on nonlinear optimization could enhance oral solutions, approximating the optimality gap. Improved draft interactions with nearby aircraft could also boost the effectiveness of the proposed solution. Thank you.